get my PowerPoint back from the current slide. I forgot to do that. Okay. All right. While we're waiting for that to come up, let me go over announcements. I think you've heard most of these before, but just in case you haven't, this is the last week of the first mini-term. Okay, I know Patrick knows that because he's in a mini-term class. I don't know if you are or not. Are you? Okay. What that means is sometime this weekend will be midterm. Okay, I don't know exactly what day and time that will be, but the first mini-term ends Friday. The second mini-term begins on Monday. You can do late registration for it up and through Monday. Now, that means coming up next week, Wednesday, 1 week from today, is when midterm progress reports are due. Now, what a midterm progress report is when we report how students are doing at midterm. Now, all they're interested in are students with D's and F's. I'd like to have some sort of work in. I've gotten from one of you, but the other, please get me either your research paper or the first test by Wednesday of next week, so I can have something, so I won't have to put another name down for midterm progress report.
I have a question. Do I need to get it to you before Wednesday, or can I get it to you on Wednesday?
Wednesday will be fine. Yeah. All right, our volleyball team, catch today's date again, is playing this evening. They're hosting Sneed State Community College. It's a home match. So it'll be over on the Birmingham West Campus, Arthur Shores Fine Arts Building, which is also our gymnasium. That match starts at 6 o'clock. So if you can go to it, they're a really good team. I think you'll thoroughly enjoy watching them play. I won't be able to be there because I'll be teaching a physics class at 6 o'clock. Okay? Now, coming up this weekend, the 11th and 12th, which I think is Friday and Saturday, is the Wallace State Huntsville tournament, and that will be up in Huntsville, Alabama, and they haven't announced days and times yet. So if you are up that way sometime this weekend, you can probably cheer them on to victory there as well. And the 15th will be next Tuesday. I'll wait for Monday to tell you about that one. Now, I've announced this several times, but I want to make sure you know about it. Okay, the first of these is today. It's the Scholarship Summit Fall 2019. Are you an upcoming graduate? You are. It may not be immediate, but you are an upcoming graduate. Do you have plans to transfer to a university? I bet so. Unsure of how to pay for the remainder of your education. You probably are rolling in the butt, so that's not an issue. Okay, come educate yourself on college transfer process and transfer scholarship opportunities available from some of the leading colleges in the state. The first of these is today from 1 to 3 over on the Birmingham West Campus, the new Academic Success Center building, the auditorium, which is somewhere in the building. I haven't found it yet, but I haven't been over there that much. But that will be from 1 to 3 this afternoon, if you're free to go over there. But tomorrow, it'll be on this campus, the faculty staff dining room, which is right next to the cafeteria, this side of the cafeteria, and that will be from 1 to 3 in the afternoon there as well. The Scholarship Summit Fall 2019 participants include Alabama A&M, Alabama State, UAH, Birmingham Southern, Jacksonville State, Tuskegee, Miles, University of Alabama Tuscaloosa, UAB, Mercer University from over in Georgia, Sanford University from here in Birmingham, Homewood area, University of West Alabama, University of North Alabama, Mississippi State University, and University of South Alabama. We'll all be here, I assume, both days. Success is where preparation and opportunity meet, sponsored by our Career Services, Counseling Services, and the Space Center. So, should be a good program. Yes?
What's the location of it on the
Birmingham?
Yeah.
Today?
Yeah.
1 to 3. You know that new building the Academic Success Center. Okay, go in there and look for the auditorium. I assume it's on the ground floor, but it may not be. But ask somebody, and they'll be able to tell you. So the auditorium of that new building there. Okay, and then the NASA's Community College Aerospace College Program will be accepting applicants through next Tuesday. I believe that's right. The 16th. Okay. No, Wednesday. Next Wednesday, the 16th. So here's information about it, websites, links, that kind of stuff. If you're interested, please check into it. It's a great program. All right. All right. I think pretty much killed that slide last time, right? I believe we're ready for example 1. Any questions before we get started on example 1? All right. Find the integral of sine cubed x cosine to the 4th x dx. What would be your approach to that problem? Here's what you look for. If they're only sines and cosines, which there are, same argument, x, they are, then check and see if either one of these is to an odd power. Yes, there is. Okay. So, what that does for you is you can separate out a sine x, put it with the dx, and that becomes your du. Okay? That's the derivative of cosine. So this is in cosine, but you still have a sine squared. But guess what, folks? We can get that in terms of cosine, right? Pythagorean identity. So that's going to do it for you. So what would be your first step? Let me get my pen set up. That'll be my first step. Okay. Well, I thought the pen would draw. Oh, there it comes. Okay. That'll be the integral of, take out one sine, and that leaves you a sine squared x cosine 4th x times a sine x dx. It looks like we didn't do anything but stretch it out. But this has potential because that sine x dx can be our du. Okay, for a u substitution. But before we do that, we need to get the sine squared in terms of cosine. So what is that? Sine squared in terms of cosine. 1 minus cosine squared x times cosine 4th x times sine x dx. Okay, we're almost there. Okay, what would you suggest we do next? Distribute the cosine 4th into the parenthetical expression. I think it will come back. There it comes. Okay? So that will be the integral of what? Cosine to the 4th x cosine to the 6th x times sine x dx. All right, now what? What you've been waiting for, what you've been setting it up for. You can do that if you want to. Let's do that. Okay, the integral of cosine 4th x sine x dx minus the integral of cosine 6 x sine x dx. Okay? Now what? That was an okay step. It wasn't absolutely necessary, but it's perfectly legal in most states. Okay? What from here? you had either one of those integrals to do, what would you have done? Say again? You will ultimately, do you want to use it as is, or do you want to do a substitution first? It doesn't matter to me. You can do it as is. You want to? Or is it clearer if you do a U substitution? That's what I've been trying to get one of you to say. Oh, yeah, okay. Let's do a U substitution. I'm glad you thought of it. What would be your U substitution? Let U equal, I'll get the first part for you. What? Help me. Huh? Not sine. What, did you say sine? You want the U to be the most complicated part. The cosine x. Cosine, this innermost part of the most complicated part. Cosine x. Then, what's next? du is equal to negative sine x dx. Perfect. Except that we don't need the minus sign. So what we'll do is either multiply or divide by minus 1 and move it out there. Okay? Now this will actually work for both integrals. That's why you didn't have to change it to 2 integrals. You could have left it at 1, but it will work for both of them. So let's do it. What is our new integral then? Minus, because that minus is out front now, u to the 4th du minus, but then you get another minus because of that minus du, the integral of u to the 6th du. Okay, can you do those two? Sure, now it's time for the power rule. What will that be? I'm going to, if it's okay, I'm going to switch them around and do the plus one first. What would that be? Okay, minus u to the 5th over 5 plus u to the 7th over 7. One other little thing. Plus c. Now go back and plug in what u is, or u are. I don't know which. It'd be. Now can I flip them and put the plus in front? Okay. You don't have to. I just prefer. Do you want your fraction out front or you want it underneath? I don't care. Which way you want to do it? Underneath, okay? So that would be cosine 7th x over 7 minus cosine 5th x over 5 plus c. That should be our answer. Oh, and they left the minus in front. Silly them. Okay. And they left it underneath, just like you suggested. Now, I have an interesting question there under the technology part, and it says, a computer algebra system used to find the integral in example 1 yielded the following, and it looks pretty different to me, okay? Oh, swimmer returns, okay. Dawson's here. Is this a mini-term course or a full-term?
Mini-term, so we're done now.
You are done? Okay. You going to take swimming too for the second mini-term? Okay. So there are computer algebra system gave a different answer, and the question is it an equivalent answer? Okay? Here's the one they gave. Minus cosine to the fifth x times 1/7 sine squared x plus 2/35, one of my favorite numbers of all time, plus c. Would you think those are at all the same? I don't know why they would give such a bizarre answer. I would far prefer this. But here's what they did. They factored out the minus cosine fifth. You see it's right there. Minus cosine fifth x. And what did you have left? A minus cosine squared x. I'm jumping the gun. Plus 1/5. Oh, that's cosine x over 7 plus 1 over 5 plus c. Okay? Now, what do you think you can do with that cosine squared? Or maybe minus cosine squared? You've already done it once. Pythagorean identity, and what is that cosine squared? So this becomes a minus cosine to the fifth x times, and what's that cosine squared? Second?
It should be sine squared plus 1, right?
Okay, if you're doing the minus with it, it would be a sine squared plus 1, okay? Let me think on that for a minute and see if that's right. I believe it is. Yeah. Sine squared is 1 minus cosine squared, so I think it's sine squared minus 1, isn't it?
Yeah.
Okay. So that would be a sine squared x minus 1 over 7 plus 1/5 plus c. I won't forget about that plus c if I don't. Okay. So this is a minus cosine fifth x. Okay. Now, times. What do we need to do here?
It looks like they split up the fraction and then
Yeah. Sine squared x over 7 minus 1/7 plus 1/5 plus c. So it's minus cosine fifth x times sine squared x over 7. That so far is exactly what they've got down here, I think. Yeah, 1/7 they call it. Okay. And then this is minus least common denominator? 35. So what would be your numerator for that? 5 over 35 plus 7 over 35. And sure enough, and then you got your plus c, that adds up to plus 2/35. Oh! No.
In the book it's plus 2.
What's that?
In the book it's plus 2.
Oh, it is plus 2. I copied it wrong, huh? Yes. I thought we did it right. Okay. Plus 2/35. Yes. So that is the same answer. The moral of that story? Don't use computer algebra system. They give you squirrely answers, but they're correct answers. Okay. Work on yourself. And I don't know why they would have given you that bizarre of an answer. Okay. But those are equivalent. And that's the problem. Yeah, okay. Question?
Now I see what I was wondering where that 1/7 minus 1 up there.
Yeah, this or this.
I was talking about on the top.
Further up here?
Yeah. I was wondering how we got the 7 squared x over 7 minus 1 over 7, but I just missed that sine squared x minus 1.
Right. Yeah. All right. Good questions. Any others? Well, let's see how they did the problem. We have done it and undone it and redone it. Let's see how they do. Let me erase my scratch. And they start with, because you expect to use the power rule, just like you were saying, with u equal cosine x. I couldn't get y'all to say that, but you did that there. Save one sine factor to form your du, which is why I was saying that's going to be your du. If you pull out one sine x dx will be your du. Convert the remaining sine factors to cosine. That's the procedure. So here's what we do. That was the original problem. Pull out one of these to get it over here with the dx. Okay? That left the sine squared here and the cosine fourth there. The sine squared you can convert to cosine because of Pythagorean identity. And that gave us 1 minus cosine squared times cosine fourth times sine x. And then when you distribute through, you get cosine fourth x minus cosine 6x times sine x dx. And there's the place I would have done the u substitution, u equal cosine x. But no, they split it, just like Patrick was saying. Okay? Then they pull out a minus sign. They do it a little square. They don't use u substitutions. They said they were going to do it here, but then they turn around and not do it here. They just make the, they do the practice of it, but they do it without naming a u. So what they did here was pull out a minus sign and negate that one. Minus sign minus is plus, so that's the same. And then that changed the sign of the second one. So all they're doing is legal. It's just it's sort of under the table. I mean, it's not, to me, as clear. Okay? And that gives them, now you do the power rule, because you got, they never did a u substitution, but they effectively did. The antiderivative of cosine fourth x would be cosine fifth x over 5. Okay? And the cosine 6x would be cosine 7x over 7. And, whoa, that's their answer. And that's the answer we got. Except I put the cosine 7 in front because it was positive. Okay. They next go to Wallace's formula, which is more than a page away. So they're skipping examples 2 and 3 and jumping to Wallace's formula. So let's go back and we'll do example 2. And by the way, this one's also at larsoncalculus.com. If you go there, you'll see an interactive version of this type of example. Okay? And here's what we're asked to evaluate now. A definite integral going from pi 6 to pi thirds, okay, of cosine cubed x over the square root of sine x. Okay? And then you got a dx here. No wonder they skipped this one. They didn't want to fiddle with it. I guess my screen will come back. There we go. Now, where would you start with this one?
You can change the numerator to cosine squared x times cosine x.
Okay, yeah, that's exactly right. Pull out one of those. Okay?
And then use Pythagorean identity.
All right, perfect. That'll be integral from pi 6 to pi thirds of, okay, you want to go on and do the Pythagorean while we're here? Okay, why not? Okay. Well, that didn't work, did it? Let me try it one more time. Okay. And when you pull out one cosine, That will leave you a cosine squared, and that is a 1 minus sine squared x. Right? And then the cosine you pulled out goes with the dx, cosine x dx, and then this is divided by, actually I don't want to put a radical. How would I write it without a radical? Sine to the 1/2 x. Okay? Now, that will be the integral from pi 6 to pi thirds. Now, let's start with the first part. We're going to split these. Okay? First part gives you 1 over sine to the 1/2 is help me. We're doing this part first. What would that give us? I don't like it in the denominator. Sine to the minus 1/2 x. Okay? Minus, and then what would the second part give you? 3/2, because that's a 4/2 minus 1/2 is 3/2 x times cosine x dx. Okay. Now, how do you want to proceed? I like that idea. So let u equal what? Sine x. Then, what? du is equal to cosine x dx. There we have our du. No SIGN signs to change or anything like that, just cosine x dx is du. So, we do have a couple things we need to do though. Since you're changing from x's to u's, you also have to change your limits on your integration, because we now are going to have a du out there, and these have to correspond to u's. So, let's pick. When x is equal to pi 6, what is u? What is the sine of pi 6? I'm going to have to fire your trig teacher. Uh-oh. I'm in trouble now. That's 1/2. Okay. And what's sine of pi thirds? Is 3 over 2. Those are our new limits for our new variable, u. And what does that new variable become? What becomes on the inside in the integrand? Pretty straightforward. U to the negative 1/2 minus 3/2. That's a half there. I'm glad you saw that. Times du. That was just your du down there. Okay, I think we may be able to do this. What is the antiderivative of u to the minus 1/2? Huh? Did someone say something? I can't hear it. A little louder. Yeah, u to the 1/2 over 1/2. Well, 1 over 1/2 is 2. Okay? I'm just going to flip that. Rather than dividing by the fractional form, multiply by the reciprocal of the fraction. Okay? Minus I know there will be a u in there. To the 5/2 times 2 over 5. Got it? And we're going to evaluate that from 1/2 to root 3 over 2. Okay, and those are substitutions for u, or values for the u. Okay, so what a mess. Okay, that will be 2 times I don't know the best way to write that. U to the well, you don't want to write it as u anyway. You want to evaluate that. Okay, that would be square root of 3 over 2, and you're taking the square root of that. So that would be the 4th root of 3 over the square root of 2. Yeah. Okay. Kind of nasty, isn't it? Minus, okay, 2 over 5 times uh, 3 to the 5th power, which I don't even want to think about. Boy, what a messy, messy problem. I know they're not going to write it like this, but that would be, again, 3 to the, here's Devin. A little time out here. Sorry, I still haven't gotten to find the things. I started going through emails this morning to look for them and just uncovered baskets of worms, not cans of worms, but baskets of worms. And I was fighting and dealing with that. So this weekend's going to be rugged, possibly early next week. I have some office hours tomorrow, but they're eaten up right now. So I don't know. Anyway, we're working on this. We're taking the square root of 3 and doing that to the 5 has powers. So it's going to be 3 to the, I think that's just going to come out 5/4 over 2 to the 1/2, 5 halves. Yeah. Okay. That's probably not the best way to write it, but that's how we're going to write it for now. Then we're going to do a minus and do the thing the other way, and that will be 2 times 1/2 to the 1/2 power. So that would be 1 over the square root of 2. Okay, I believe. And then we're going to do a minus, which is a plus 2/5 times 1/2, well, 1 over 2 to the 5 has power. Okay. What a mess. Now, I don't know. Right off the top, I'm going to say root 2 into 2 is going to be root 2. Okay? Are y'all okay with that? So I'll do it there, and I'll do it here too. I'll wipe out this and put that at root 2. Okay? Let's see how they write their answers. They didn't go to that much thing. They just left it as 2 times the square root of 3 over 2 to the 1/2 power minus 2/5 the square root of 3 over 2 to the 5/2 power minus 2 times 1 over 1/2 to the 1/2 power plus 2/5 1/2 to the 5/2 power. Okay. And that would be okay to do it. That's how they left it. Except except they sort of evaluated some on the second part. This one they did change the root to, just like I had done. They didn't do it out at front, but they did it there. Okay, and then the second part, 2 to the 5/2 power there in the denominator, and a 2 to the 2/2 power in the numerator would be 2 to the 3/2 power here over 5. And 2 I'm not sure they got it right. Okay. 2 cubed is 8. So I get the square root of 8 there. They got the square root of 32. I may have done something stupid, but I don't think so. Oh, yes, I did do something stupid. No? Well, number one, that's to the minus 3/2 power. So yeah, I did do something stupid. I don't know. I don't get their last part there. 2/5 of 1/2 to the 5/2 power, the 2 to the 5/2 power, and 2 to the 2/2. Oh, I know what they did. Okay. I don't know why they did it, but they did it. Okay. 2 to the 5th is 32. So that's in your denominator. Okay, I see what they did. Let's just work with this one down here. 2/5 times 1 over 2 to the square root of 2 to the 5th. Okay, right? That's what you have there. All right. Why they went back, I can't figure this out. Why they did it, but they did. So this would be 2/5 times 1 over the square root of 32, right? So let's multiply by the square root of 32 here and the square root of 32 there. So that gives me 32 down here, okay? Okay, 32. 2 will go into 32 16 times. 5 times 16 is 80. So that gives me a root 32 over 80. Yeah, that was worth it, wasn't it? So that is the right answer, or a correct answer. Why in the world would they go to that extreme if you kept everything else, and you can find it now, like this? Why would you read that like that? No, let's get that to some sort of radical form, and it's fine. It's absolutely correct, but it just doesn't look anywhere close, but it is. Okay. So that last term up there is a root 32 over 80. Okay. that's one reason I don't really care that much for the WebAssign. It does have tutoring help. It does have all sorts of good things on it. But it tells you there's one and one correct answer. And if this would have been the correct answer, I would have probably worked all day long and never come up with that answer. Okay? I would have gotten all sorts of other forms that were correct answers too, but they would say no, wrong, 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 until you came up with that. And I'm not sure I would have ever gotten that. So I would have either, if I'd have been very confident in what I was doing, I said, well, I think it's the same. But I don't know what their answer is. But I think mine's right. Or if I hadn't been so confident, I'd say, what am I doing wrong here? And you're doing absolutely nothing wrong. You just haven't got the last answer to their form. Sorry about that. That's my little soapbox I'll get out. All right. That was example 2. Any questions on that? We did get the same answer. It just doesn't look at all like it. Now, they also give the decimal representation, which is fine too. Okay? So, anyway. All right. Any questions? Example 3. I love it when they give examples that are so simple. Okay. You can get lost in the sauce trying to figure out their complexities, and you don't know if you got the whole purpose right. Uh-oh. What about example 3 here? Find the integral of cosine 4th x dx. What can we do with that? Besides erase it, don't even tell me that, okay?
Could you do factor?
How?
Do cosine 2x times cosine 2x.
Okay, cosine squared x times cosine squared x. Okay, yeah. Perfectly legitimate thing to do. This is cosine squared x. Can I just go on and make that squared? Will you accept that so I won't have to write as much? You're always looking out for my benefit, right? Okay, good. Good man. Okay. Now, how does that help anything? Do you remember what we did last time in what they call the power reduction formulas? Oh yeah, we remember that, don't we? Remember how that goes? It's not too bad to go back and recreate it if you don't remember it.
It's 1 plus cosine 2x over 2.
Okay. Say that one more time.
Is it 1 plus cosine x over 2?
Cosine 2x, I think, over 2. And then that's going to be squared, dx. Okay? I don't memorize well, so I'd have to go back and verify that, but I believe that's correct. Okay? Because it's a, you got sine squared plus cosine is equal to 1, and cosine squared minus sine squared is equal to cosine 2x. So if you were to add those two together, you lose the sides, and you get 1 plus cosine 2x. Yeah, 2 times cosine squared x is equal to 1 plus cosine 2x, and then divide by 2. Yeah. So what do we do next? It's kind of a big boo hiss here. You have to, I'm going to pull out the 1/4. Is that okay? Because you got a 2 in the denominator that you're squaring, so I'm going to pull out a 1/4. And now you have 1, square that binomial. Help me. I'll even put the plus sign. Square 1 plus cosine 2x. 2 cosine 2x, right? Plus squared of 2x. Okay, got it. Okay, dx. Okay, I can do the first and the second one of those without a whole lot of help, but some help. Okay, I'm going to ask you for help. And that would be 1/4 times the integral of dx plus the integral 2 times the integral of cosine 2x dx plus the integral of cosine squared 2x dx. Okay? But what do you notice about that third integral?
It's to the second power.
Second?
It's to the second power.
It's to the second power, and so therefore we got to do the same thing again, because it's a cosine squared. So what will that become? But now we just do it to the first power. Excuse me. Third integral will be 1/2 1 plus cosine 2 times 2x, right? dx. So that would be 1/2 the integral 1 plus cosine 4x dx. Now what would that be? 1/2 the integral of dx, which is x. And how about the next one? Antiderivative of cosine 4x plus sine 4x, but you got to undo a chain rule type thing. Divided by 4. All right, that's the end of that one. Okay. I should put that bracket there. This one would be what?
Wait, which one?
This one right here. That integral. This one.
Sine of 2x.
Sine of 2x, and I think you can leave that alone. Sine of 2x, because when you take a derivative of that, you get cosine 2x times 2. You already got the times 2 there, so that's okay. All right, that's a plus there, and a plus in front of this, and this gives you an x, and then you have your parentheses, bigger parentheses, and here's your 1/4 in front. Okay? Now, what's your final answer? You got a 1/4 x and 1/4 over 1/2 of an x, so that'd be 1/8 of an x. So 1/4 x plus 1/8 x is 3/8 x. Agreed? Okay. Plus, and here you have just a 1/4 sine 2x, right? And then you have a 1/4 of a 1/8, which is a 3/8. 1/4 of 1/2, I'm sorry. No, I'm sorry, that's not a 3/8, that's a 1/8. Right? 1/4 times 1/2 is 1/8. I already dealt with the x there. But then you have another 4 in the denominator, so that becomes a 1/32, doesn't it? Look at all these denominators. A 1/4 here, a 1/2 here, and a 1/4 there. that would be 1/32 times the sine of 4x and something else plus c. Now, I don't know if that's how they leave it or if they factor out a 1/32 and have a bunch of other things in there. Let's see how they leave it. Oh, they do 3/8x, only they do 3x over 8, which is fine, plus sine 2x over 4, that's the same as 1/4, plus sine of 4x over 32, plus c, I'll buy it. But if you're in Advanced Web Assign, they're going to want you to put those denominators where they did, and they will say, no, this is the wrong answer. When that's a perfectly correct answer, you just have the denominators up front rather than underneath. So I'm fine with it, even though it doesn't sound like I am. Okay. It said in example 3, when you evaluate the definite integral from 0 to pi halves, so let's just pretend this was a definite integral. 0 to pi halves, 0 to pi halves, 0 to pi halves, 0, I put it in the wrong place, 0 to pi halves, 0 to pi halves, 0 to pi halves. We haven't done any substitution, so they say 0 to pi halves. Okay. Then every one of those we have to evaluate from 0 to pi halves, and we'll leave off the plus c. So let's do the pi halves part first. You put a pi halves in for x, what do you get? Three pi 16ths, 3/16 pi, something like that. Yay? Yay, all right, good. Plus, what is this? Okay, what is 2 times pi halves? Pi. What's the sign of pi? 0. Okay. Ooh, okay, I can buy that. How about 4 times pi halves? 2 pi. Sign of 2 pi is? Also 0. So that looks like our answer right there. If you subtract the zeros from it, 0 would wipe out the first one, wipe out the second, wipe out the third one, so you just get 3/16 pi. So it says, note that the only term that contributes to the solution is 3/8x. That observation was generalized in the following formulas developed by John Wallace from 1616, who lived from 1616 to 1703. Now, he was, I'm pretty sure, I'm not absolutely certain of this, but I'm pretty sure he was the Lucasian professor of mathematics at Cambridge University. Along came a student who studied under him. Anyone guess who that may have been? Isaac Newton. So when it says here, Wallace did much of his work in calculus, even though it wasn't called calculus yet, prior to Newton and Leibniz, and he influenced the thinking of both of those men. He's also credited with introducing the present symbol, the sideways 8 for infinity. Okay, you can go to larsoncalculus.com to read more of his biography. If any of you are interested in following up on that, he's a potential paper topic. This cannot be this could be your source of your idea, but it shouldn't be your source of your paper. Okay. But what I was saying is, I'm pretty sure he was the generation just before Newton. And he taught Newton, I think, about all he could teach him, and then resigned his chair so Newton could take over, because Newton was obviously way past everybody else around. So he actually gave up his chair so Newton could take over. So let's go to the next slide, which is this. Wallace's formula. N is odd. Okay? Now this is only talking about the integrals of cosine raised to a power. Okay? If n is odd, we're just going to, that's 3 or greater, okay? Greater than or equal to 3. We'll pull out one of those cosines and then the rest of them as 1 minus sines, okay? And you can go through it. You're integrating from 0 to pi halves, and you'll find out you get a product, and if that n was just 3, that's there, it'd be 2/3 would be your answer. We can do it and see. If it's 5, it would be 2/3 times 5/4. And you keep doing, and it just keeps multiplying up until you get to your n minus 1 over n. If n is even, that's what we were just doing, then it would be 1/2 times 3/4 times 5/6. Now this n is greater than or equal to 2. When it's equal to 2, you get a 1/2 equal to 4, which is the one we just did. You get a 1/2 times 3/4, which is 3/8, and we multiply that by pi halves. These are not multiplied by pi halves. This one is. Surprisingly, you get the same prefix here, and that just whatever your n is, n minus 1 over n. And you multiply all those together. Those formulas are also valid when cosine nx is replaced by sine nx. Now you might wonder why that's the case. If you think about area of this, let's just do a simple cosine. It starts at 1 and goes down to 0, right? That's the graph of it, from 0 to pi half, right? Think of what sine is. It starts at 1 and goes up to, it starts at 0 and goes up to 1. Hey, those are the same areas. Sine and cosine curves are just exactly the same, so this will also work for sine nx. Same formula will work for them. Now, how in the world Wallace came up with that before calculus was even invented beats me. Pretty incredible observation there. Had to have been a pretty sharp dude in math. All right. So now let's move to intervals involving secant and tangent. Okay? And here are the guidelines for secant mx, tangent nx. These are to the nth power and the nth power. Okay? When the power of the secant is even and positive. Okay? Now, I think before I said we're always going to deal with positive. No, we're not. Remember that when we had the square root of sine in the denominator? That was a negative non-integer. Okay? So we can have that. But when the secant is even and positive, we save a secant squared out front. Okay? And then you have, if that power of secant was even, okay, you pull out a secant squared, then it's either going to be 0 to the 0th power, which is just 1, or it's going to be just some still even number, right? So you have a secant squared, convert the following secant squareds to tangents, or tangent squares, because Pythagorean identity. then expand and integrate. Because you got tangent to the end, it doesn't matter if the end is even, odd, positive, negative, fractional, it doesn't matter if that secant was even, integer, and positive, okay, then you can do that. So if it's even, then you can write that as 2k, and that would be a secant of squared. This is a weird way to write it, but it is indeed true. Secant squared to the k minus 1. In other words, that's secant to the 2k minus 2, because you pulled out a secant squared here. But now this is secant squared to k minus 1. Secant squared can be written as 1 plus tangent squared to the k minus 1. And your tangent is just hanging there. You know, it just keeps there, tangent to the end. And they left it there, but at this point, you do you distribute across here. So it raises to whatever power you need, that k minus 1 power, okay? Do that, multiply, distribute the tangent in across that. However weird that was, it's still doable. And then you do a u substitution, let u equal tangent x, and du is secant squared x, dx. And it's done. Now, when this power of tangent is odd and positive, save a secant tangent factor. Okay, remember, secant tangent. If tangent's odd, save a secant tangent. That leaves the remaining tangents being even, okay, and convert the remaining secant m, that can be anything, tangent 2k plus 1, that means it's odd. Pull out a tangent, and that leaves you a 2k. Pull the 2 inside and do the k on the outside, and this you have secant to the m minus 1, because you also pull one of those over here. That's going to be your du for secants. The derivative of secant is secant tangent. So you pulled one of these out of here for secant, and this could have been positive, negative, fraction, decimal, anything. You can still subtract 1 from it. This needed to be integers, positive, odd integer. Pull one out, and then you have a tangent squared to a power. Tangent squared is secant squared minus 1, raised to that kth power, multiplied by this thing. So this part, when you distribute this is doable, that's doable, and then everything's in sort of terms of secant. Derivative of secant, secant tangent. So again, you have a good u substitution there. Okay. Now, when there's no secant factors, okay, in fact, all you got are tangents, the power of tangent is even and positive. Power factor. Now, when it says even, that implies it's an integer. Okay? No secant factors, power of tangent is even and positive. Convert a tangent square factor to a secant squared factor, Pythagorean identity, okay? And expand and repeat as necessary, okay? So pull out a tangent squared, that leaves you a tangent of n minus 2, but n, remember, is even, okay, and positive. And this becomes a secant squared minus 1. Okay. The tangent of this, secant dx, secant squared of that, this is the derivative of tangent, so you can do a u substitution on that part. This part, you keep going. Then you have a minus tangent to the n minus 2. That's still an even number. Pull out another tangent squared, do another. So you keep doing that until you run out of tangents. Could be tedious, but it's not too bad. Now, when the integral is of this form, secant to the m, no tangents in there, m is odd and positive, do integration by parts. Whoa, how does that help you? Okay. I'm sure they're going to show it to you later. So we'll hold off on that for a minute. We're going to see how that works later. And then number 5, when the first 4 guidelines do not apply, try converting to sines and cosines. Okay? If all else fails, go to sines and cosines. Okay? If you can't use the Pythagorean identity, go to sines and cosines. Okay? So, some of their examples I'm sure are going to hit just about every piece of that. All right. Yes?
In the book it says number 4 is illustrated in example 5 in section 8.2.
Yeah, that's going to be example 5 coming up. Oh, wait. In 8.2. Ooh. I've forgotten that. Did we do that? Yeah, we had a secant cube there. Okay. And, yeah, we said it's magic. Yeah, but we did the that back on page 527. Yeah. So we have already done one of those. Okay. So let's do example 4. What would be your approach to this one? Number 1, don't write it with radicals. And don't write it with denominators. How would you write it? Tangent cubed x times secant to the second 1/2 x dx. Okay. Now, if you look at your guidelines there, number 2 is when the tangent is odd. And it doesn't matter what secant is, tangent being odd. Pull out a tangent, but a tangent isn't a du, you need a secant tangent, okay? So you're going to subtract 1 from each of those exponents. So that will give you a tangent. You pulled out 1 tangent, and what you got left? 2 tangent squared x times secant, and you subtract 1 from minus 1/2, and you get minus 3/2 x. And then what you have there is that tangent you pulled out goes here, tangent x. The secant you pulled out goes here, secant x dx. Okay? Now, 2 things to note. First, tangent squared can be written as secant squared minus 1, secant squared x minus 1 times secant minus 3/2 x times tangent x secant x dx. I'm going to get tired of writing all that stuff down, but I'm going to take it in gory detail here. Okay? First of those is going to be what? When you distribute the secant to the minus 3/2 with the secant squared, what do you get there? Squared is 4/2, right?
So, to the 1/2?
To the 1/2 power, minus secant, you're not doing anything to that one, to the minus 3/2. Oops, I forgot my x. X. And then we've got tangent x secant x dx. Or you could have written the secant x first if you prefer that, because what are we going to do now? Set up right ready for it. Let u equal what? Help me. Secant x, you got it. Then du is equal to secant x tangent x dx, which is exactly what you got there. So let's write down the new integral, and what will that be? U to the 1/2 minus u to the minus 3/2 times du. Got it. I think we can even do that, can't we? What does that give us? Oh my goodness, the 10 o'clock scholar. All right. That's a little more like an 11 o'clock scholar, or 11:15 scholar. Yeah, okay. Y'all don't remember that nursery rhyme, do you? So, huh? A dill or a dollar, a 10 o'clock scholar, why do you come so soon? You used to come at 10 o'clock, and now you come at noon. No, okay, it's just a nursery rhyme. Not that it applies here or anything, but okay. Antiderivative of u to the 1/2. I write down the u part. Come on, power rule. U to the 3/2 times 2 over 3, or divided by 3/2 if you want prefer it that way. And the next part would be okay, you didn't put a sign in there, did you? Okay, you could put a minus u to the negative 1/2 second. No. Yeah. You change that minus to a plus and put a 2 there. You're absolutely right. Okay. And one more little thing. Plus c. All right. Now we go back and substitute in secants there. And I don't have much room to write. I'm going to write it up here. That'd be 2/3 secant to the 3/2 power x plus 2 secant to the negative 1/2 x plus c. Now that's one way to leave it. Let's see if that's how they left it. 3/2 secant to the 3/2 power plus 2 secant to the minus 1/2 power plus c. All right, good deal. That's how we did it. You want to see how they did it. Any questions for our race? Or right over? Any questions? No? All right. So how do we begin? Because you expect to use the power rule with u equals secant x. I love the way they do this. They say the power rule and then don't use it. Let's see if they'll use it this time. Save a factor of secant x tangent x out of there. Now, why were you anticipating using u equals secant x? Well, because you could pull a tangent out of tangent cubed, and that would be a derivative of secant. And the most complicated part of this problem, the innermost part of the most complicated part is that secant. That's what you want to be the u. So that's why you pull out the tangents, okay? A tangent and a secant, okay? And convert the remaining tangents to secants. That's the other reason, okay? So that's going to be, and again, they wrote it secant to the minus 1/2 tangent cubed dx. just like we did. Just rewrite. Okay? Then they're going to pull out, and that leaves, pull out the tangent out of here, secant out of here. That leads you to the minus 3 halves. Put the secant here. They pull out a tangent here. That leaves you tangent squared from there. They call it another rewrite. It is, but setting up for this to be your du for your secant x. Well, you got a secant x here to a weird power. You got a tangent squared, which we can convert to secant squared, Pythagorean identity, and here you have that d-secant. So let's see what you get. That's the integral of secant to the minus 3 halves x. Whoa, they left, no, so they put secant x in here to the minus 3 halves. And your tangent squared became secant squared minus 1. And then this became your secant x tangent x. Trig identity. Pythagorean identity, in fact. And then when you distribute this, that gives you secant to the 1 half, just like y'all did, minus secant to the minus 3 halves, just like you did, times your d-secant, okay? Secant x tangent x. And that's exactly what they did. Oh, they just skipped it all. They said integrate, this is what you get. Okay, wasn't that fun of them to do. This is a d-secant, so this is secant to the 1 half does secant to the 3 halves times 2/3. This is a secant to the minus 3 halves, that will become a secant to the minus 1 half times a minus 2, so that gives you that, plus c. And I guess that's how they leave it, isn't it? Yeah, I guess they do. And proceed to skip example 5, example 6, example 7, and then they pick up there. All right. So let's back up and do example 5. Find the integral of secant 4th x. No, secant 4th 3x. What are you doing? My pen isn't writing. So aggravating. There it is. 3x. Secant 4th of 3x. Tangent 3rd of 3x dx. Don't know about you, but this smells like a double substitution. I would say U substitution, but probably don't want to use U for both of them, so something else. All right. What is the, what guideline do we use here? First guideline was if tangent has an even power, it doesn't. Second guideline, if tangent has an odd power, pull out not just a tangent, but a tangent and a secant. Okay? So basically the same thing we used before. So this will be what? Rewritten, this will be a, I'll write down the secant, you tell me what power. I pulled out one. That will be 3rd 3x times a tangent. Help me. Second squared 3x, and the secant I pulled out goes here, secant 3x, and the tangent I pulled out, tangent 3x dx. Woo! Now, we might be able to get by with one, but let's see. What do we do next? You notice, by the way, this is related to the derivative of the secant, right? So we like having secants here. We don't like having tangents there. So what do we do? What do Pythagoras think about?
One of the trig identities.
Second?
One of the trig identities.
Yeah. Which one?
Secant squared x minus 1.
That's it. Okay. So secant cubed 3x, and rewrite this as secant squared 3x minus 1 times, I want to just go on and say d secant x, but let's leave it here. Secant 3x tangent 3x dx. Okay. Next is your distribute step, and that gives you what? What does that give you?
To the 5th power?
Second to the 5th?
Yeah.
5th power 3x minus 3rd power of 3x times secant 3x tangent 3x dx. Okay. Now we're trying to figure out what we do with this. Okay. What you reckon you might let a u substitution be? Second? Not tangent. Everything's in terms of secants here, isn't it? That's where we're ultimately going to go with secant.
Let's do secant 3x. That's our use.
Okay, let's try that and see what we get. Let u equal secant 3x. Now, if that's what you said, I don't hear well, so I may have messed up. Okay, then what? du is equal to secant 3x tangent 3x d of 3x. And what's d of 3x? 3 times dx. So I'll write that as secant 3x tangent 3x, put the 3 out front, and then put the dx here. Okay, we don't want the 3 there, so let's divide it out and move it over here with the du. All right, now I think we're ready to roll. Okay, I think this will be a 1/3, that's from your du over 3. This last integral is the one we're substituting. That would be the integral of what? U to the 5th, U to the 3rd, du. Okay, I think even I probably could do that one, but help me. What would that be? U to the 6 over 6 minus 4th over 4. Okay. You could do a plus c now if you want to. You could wait and do it later. I really don't care that badly what it is going to be, but I think your answer is going to be 1/18 secant to the 6th power of 3x, okay, minus 1/12 secant to the 4th power of 3x plus c. I can think of several ways they may want to rewrite that. Let's see what they did. Example 5. Well, whoa! I'm sorry, I misstated the first one. We should have used the first, or we could have used the first one. But this, what we did was absolutely correct. Let's see if these are indeed the same answers. This is going to take way too long, I think. We got our coefficients right looking, okay? They have a plus where we have a minus. I think it'll all work out if we do the Pythagorean identity. It's just I don't think we're going to have time to do it all. You want to try it real quickly? It's not going to be real quick, okay? This is going to be secant squared 3x cubed, and that's going to be a 1 plus tangent squared cubed. No, it's not going to be quick, but I'm convinced they are the same answers, okay? I probably can't convince you of that real quickly. Are you going to buy it or not? Do we want to go back and do it? But that is a correct answer. We should have done this tangent substitution, pulling out a secant squared. I wasn't paying attention. Okay? That would have been maybe a tad easier, but really comes almost the same. I mean, almost exactly the same. But it says in example 5, the power of the tangent's odd and positive. You could also find the integral by using the procedure decided in the second guideline. That's what we did on the previous page. And then exercises 67, 68, you're asked to show that results obtained by those two procedures differ only by a constant. And so you can incorporate that constant into C. Okay. And I think we've run, yes. Oh, is that this? Yeah.
When we do the du, why is it d3x?
I'm sorry?
When we do the du earlier in the problem, why is it d3x?
Okay, because right here, I think it was, right here, here, because when if u was this, okay, derivative of u is derivative of secant, and then chain rule derivative of the inside. Is that enough of an answer? Yeah, that's why. Because of the chain rule. I'll just leave it like that. Because that's what we did. Chain rule. And we didn't want a 3x there, we wanted the dx. Yeah. Good question. And I believe that we're basically out of time. I don't think we'll anywhere close to having time to do number 6 here. So let's start with 6 next time. And homework exercise. Oh, we almost finished 8.3. Do any of the odds 3 through 13. They're all at Calc Chat. 7's at Calc View. Do any of the odds 15 to 19. They're all at Calc Chat. Do any of the odds 21 to 33. They're all at Calc Chat. 27's at Calc View. You can try doing 35 or 37. They love to throw in these differential equations, even though that's a different course. But all you're doing is integrating, so you can do that. They should be at Calc Chat. Then they do the slope field, which usually is that differential equations course. That's 39. I think you can do that. And 41 is the slope field. Stop there. We're picking up with 43 next time. We'll do a couple more. And if some of the ones in, say, 21 to 33, you get a little stumped on, hang on, we're going to do a few more examples like those, and that probably will give it to you. All right, good deal. Any questions? I think today we were totally in 8.3, weren't we? I think we started almost at the beginning. Yeah, 8.3. So have I cheated